In this video, we're going to look at quantum mechanics and how it relates to the atom. But to start with, we're going to just dip our toes into quantum mechanics by learning about Schrödinger's cat. So, in classical physics, a thing is something or it isn't. And what I mean by that is that a ball is on the ground or it isn't on the ground. It can't be both. A cat is alive or a cat is dead. I don't need to look at it to confirm it is dead or alive. It either is or isn't. It doesn't matter what I do to look at it. Quantum mechanics is not like that. Basically, in quantum mechanics, the ball would be on the ground or in the air, or I should say, and in the air, until I looked at it, and then it would either be on the ground or in the air. And so how that relates to a cat, so in Schrödinger's cat, the cat is both dead and alive at the same time, and it's not until I look at it does the cat actually become dead or stay alive. And so the way that Schrödinger first talked about that is that atoms can emit particles as we saw it, and until you look at the atom is emitting and not emitting the particle at the same time. And quantum mechanics is crazy unless you're dealing with stuff that is as small as an electron. So let's talk about quantum mechanics and the atom now. For electrons, position and velocity are complementary. That is, you can tell where an electron is, but you can't tell me how fast an electron is going or what direction. Or you can tell me how fast an electron is going in what direction, but you cannot tell me where it is. You can only know one of those things at a time. So if we know the energy of an electron, the velocity, because velocity is equal to energy, then I can predict based on probability where the electron is, but I can't say for certain I know where it is. It's just some of those crazy statements that make up quantum mechanics. So let's look at the equation Schrödinger has to help us predict where we can find an electron based on the energy that electron has. And the solutions from Schrödinger's equations are called wave functions, and that's what the symbol of the wave function is. Now, if you plot distance from the nucleus versus the wave function squared, you get what's called an orbital. An orbital is just a region around the atom that you're saying, okay, in this area of space, you are most probable to find an electron with energy equal to some number. So here's a picture of orbitals. So for example, this sphere, this S sphere, if you solve a wave function for this and you plot this versus distance, you're saying in this sphere I'm going to find an electron. Here are p orbitals. You're saying in this sphere I will find an electron, or in this sphere I will find an electron. You're just saying in these regions it is probable. You can't pinpoint exactly where it is. You can just say it is probably there. Now to solve the wave function, you get three terms, and that will tell you what is the size of your orbital, that is how far out from the nucleus it is, what shape is it a sphere or is it those blobs that we saw in the previous picture, and what orientation does it have, or in other words, what axes does it have, where in 3D space does it look. Okay, and these different variables we call them quantum numbers. We have principal, angular, and magnetic. So N, L, and M sub L. There's actually another quantum number called M sub S, which is spin. We're not going to learn about spin. If you ever take a physical chemistry class, that's where you're going to learn about spin. Right now, we'll only focus on N, L, and M sub L. All right, let's learn about N, your first quantum number, your principal quantum number, N. And all N says is your electron has this amount of energy. Remember in the Bohr model, we saw that electrons had some kind of energy. The further they were away from the nucleus, the higher energy they had. You can think of the same thing here. If a electron has a quantum number n that is equal to 1, it is the lowest energy state. If it gets a higher quantum number, like n of 2, 3, or 4, it goes higher up in energy, more positive. And when we talk about energy, negative energy or low energy, good, positive energy or high energy, bad. So your integers, the lowest you can go to 1, and then you can go to infinity, 1, 2, 3, 4, so on and so forth. So the larger value of n, the more energy an orbital has, and so the more unfavorable for the electron. And all our energies here are negative. Okay? So if an energy is 0, the electron escapes the atom. So energy can't be positive. Once an electron's energy is 0, it is no longer attached to an atom. And the larger value of n, the bigger our orbital is. The bigger space we have to consider to say the electron is here, 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 here. Our probability starts getting worse and worse. And as our n gets larger, the energy separating these different levels gets smaller. So let's look at the gap between 1 and 2. That energy gap is huge. 2 to 3 is smaller. 3 to 4, smaller still. So as you go up higher in energy, the energy between your gaps get lower. And we can calculate the energy of each level through this equation, where energy at level n equals this constant multiplied by 1 divided by n squared. And this is why the energy gaps get smaller and smaller. 1 divided by energy level 1 versus 1 divided by 2 squared, which is 4. You go up something like 3 and 4, this number becomes smaller and smaller and smaller. Alright, so that was n. Our next quantum number is L. This is just basically what the shape of your orbital is. L has values of 0 to n minus 1. So if n was equal to 1, which is our principal, we will have a 0 to 0 range. If n was 2, 2 minus 1 is 1, our range would be 0 to 1. If n was 3, 3 minus 1 is 2, our range would be 0, 1, and 2, so on and so forth. Each value of L that we have, we give it a particular letter so we can remember the shapes easier. So if we have an L number that is 0, we call that S. S are spherical, that's why we give it S orbitals. If it's P, it looks like this figure 8 and or 2 balloons tied at the knot. That's for L equals 1. We get a P orbital. If L equals 2, now you get like 2 figure 8s that cross each other, or 4 balloons that are tied to each other. So that's what d orbitals, or if your quantum number equals to 2, that's what it looks like. And we have one more, L equals 3. You get really weird looking structures when you get to L equals 3, or F orbitals. It's like 8 balloons tied together. We're really going to focus on S, P, and D in this class. If you go into organic and physical chemistry, that's when you'll look more at the F orbitals, or L equals 3 quantum number. The last quantum number we're going to talk about is m sub L. That is, what direction or where in 3D space does your orbital point? So these values are from minus L to plus L. So for example, if your L value is 0, your range is 0 to 0. However, if your L value is 2, your m sub L values are minus 2, minus 1, 0, plus 1, and 2. So when L equals 2, which is your d orbital, you have 5 orbitals now. So for me, this is really easy to think of for P. The P orbital has an L value equals 1. So it ranges from minus 1 the 0 to +1. Therefore, you would expect 3 orientations, and we do. We have one orientation that goes along the x-axis. We have one orientation that goes along the y-axis, and one orientation that goes along the z-axis. That's what we're talking about when we say orientation of the orbital. So if I want to talk about an orbital, I have to have 3 values. I have to know the principal, or n. I have to know the angular, the L, and the directional, m of L. And now, when we talk about orbitals as a whole, we have some vocab to go with that. So if orbitals have the same value of n, we say they're in the same principal energy level, or in the same shell. They are in the same shell of the atom. And if they have the same values of n and L, they are in the same sublevel or the same subshell. Okay, so let's try and do some hands-on activities with orbitals. Let's say you have an orbital that is n equals 2. What orbitals can you have from this n, L, and m sub L values? And for these, draw what these look like. So go back to the previous slides. See if you can figure this out. Do a little bit of drawing. Come back when you have an answer. Alright. So we know L goes from 0 to n minus 1. So you can only have 2 values. 0 and 1. M sub L goes from plus to minus L. So our highest L number is 1. So it would be minus 1, 0, and plus 1. So let's say we have n equals 2, L equals 0, m sub L equals 0, you get a sphere. L equals 1, m sub L of minus 1, 0, and 1, you get your p orbitals along the different axes. Now you might need a little practice to get this straight, but once you get the rules down, it's just a couple of rules you have to memorize. You have to memorize what the L shapes look like, and you should be good to go on orbitals. And remember, orbitals are just an area of space where you're likely to find an electron. Okay, that's it for this video. I will see you in the next one.